Inductive.
Oh, is that what it was? Okay. Did you know that Descartes had to do with some mathematical things? Has any math teacher talked about Descartes? Okay. Do you know what they call this system of 2 over 3 up? What's that called? Cartesian coordinates. That's from Descartes. Get that? So Cartesian coordinates. Anyway, so Rene Descartes and Isaac Newton, they figured out that there was a mistake with Galileo. It was a tiny one, but so they kind of straightened out his idea of inertia, and that's why Newton's first law of motion is the law of inertia. An object at rest has a tendency to stay at rest. An object in motion has a tendency to stay in motion in a straight line at a constant speed. Now, so even an object going in a circle has no tendency to keep going in a circle. Have you ever had like a ball on a string? Have you ever done anything like that? And so the string is keeping the ball from going somewhere, isn't it? So the string keeps doing this, pull, pull, pull. And the ball keeps going to go, I'm going to go off in a straight line. No. And then if you let go of the string, what happens? Does the ball really keep going in a circle? No. Not one ball. What if I had 2 balls? That'd be interesting, isn't it? Have you ever seen that? You ever seen something had 2 balls on it and you throw it and it goes? Then the center of gravity has a tendency to go off in a straight line. You ever see that? Okay, so I just wanted to bring that up because it's kind of neat stuff. Anytime you talk about Galileo and Newton, you're talking about the world. You're talking about what's out there in that real world that you live in. Okay. We also mentioned yesterday that there were 2 equations that were used for acceleration. And last chapter, what was the equation that would be used to find acceleration? Do you remember that one? What was the equation used last chapter for acceleration? Yes. Right, excellent. Change in velocity over time, yes, that's right. And to find a change in velocity, it was the final velocity minus the first velocity over time. And if it came out to be a negative number, what did that mean? That you were slowing down. It's still acceleration. It's negative acceleration, and humans like to call that deceleration, don't they? And then if it came out to be a positive number, then it was said you're speeding up, right? You also know that if an object's at rest, or if it's moving in a straight line at a constant speed, what is the net force on it? 0. And so this chapter says there is another way to find acceleration. It's Newton's second law, F equals ma. But I'm going to rearrange the equation and solve for a. What is the cause of acceleration? This tells me how to calculate acceleration, right? But you better give me these 2 numbers in time, or I can't do it. But what if I don't give you these 2 numbers? What if I don't know the speeds? Is there another way to find acceleration? Yes, if you give me the force on the object and its mass. And so here's what Newton's second law is, F equals ma. And so now, if you take the force and divide it by mass, you'll get how much the acceleration is. Now, what's tricky are the units. What are the units for force? What are the units for force? Do you remember? A Newton, is that right? A Newton? But a Newton is a kilogram meter per second squared. Well, I just said that, let's take a look at this. I'll even show you how to memorize this. How do you memorize what a Newton is? F equals ma, right? What is the SI unit for mass that we're supposed to use in physics? The kilogram, okay? And what is the unit for acceleration? We just had a whole chapter on that. That's not good. What is it? Meters per second squared. Isn't that right? Isn't that acceleration? So what would you have, MA? What if you took kilograms times meters per second squared? What would you get? Kilogram meters per second squared. And that is going to be a force unit, which is called a Newton. So that's how you can memorize what a Newton is. But a while ago I asked you, it says A equals F over M. What kind of units would you get there? Well, here's a Newton, kilogram meters per second squared, and here is mass is kilograms. What happens? These cancel out, and I'm left with meters per second squared. Does that sound like an acceleration unit to you? Wow, this all works out, doesn't it? Now remember, when I was younger, they didn't make me keep track of my units and things like that. I just liked math anyway. But it really hurt me later when I was trying to understand it, because I didn't know what the units were. And nobody made me do it. And I got to college and I got killed. I got killed because it didn't make sense to me. I didn't understand how to make sense of the units because nobody made me make sense of the units. If the units don't make sense, you probably made a mistake. You got that? All right, yesterday, didn't we do these 3 problems? Do you remember those? Now, if I give you this tomorrow, you could do it, can't it? If it says here, the mass of a car is 1,000, what's the acceleration? You're going to give me mass, you're going to give me force, you want me to find A. I wonder what equation has F, M, and A in it. What do you think? Is that Newton's second law? All right. So I'm going to use that equation for acceleration, aren't I? And then what about this one? Find the force. If the force is 4,000, we could plug it in again, couldn't we? And then we did one over here. So if you look at this and you just kind of look at it tonight, if you have a chance, look at the units and say, yeah, that makes sense to me. All that makes sense to me. All the units do. All right, next. I won't talk too much about this. It's actually, I have very few questions on that. I don't have any questions tomorrow, but I'll wait till we have the test on chapters 6 and 5. But if you read this part here, what is friction? What do you think friction is? Friction is what? Anybody have an idea? If you have to tell somebody, what would you say, Alistair?
Resistance to movement when between 2 objects.
Now, do you think, how would you classify friction? What kind of units would you use? What would you classify it as? And I'll give you a clue, okay? In another chapter, I said, what if you had a box and you were sliding it along the floor, okay? And what if you knew you were pushing a box with 30 newtons of force? And what if the box was going at a constant speed? What do you know about a box that's moving in a straight line at a constant speed? What do you know? Very good. Net force is what? Now, if the net force is 0, how can the net force be 0 when I know I'm pushing the box with 30 newtons? How can it be a net force of 0? And you have to start asking yourself what? There must be another force of 30 newtons in the opposite direction. Does that make sense to you? I mean, that's not something you wake up and say, I knew that from birth. No. Isn't that right? You have to think about this, don't you? So guess what? What direction is friction always in? Ooh. First of all, it's a force measured in newtons, right? And what direction is it always in? Opposite of motion. If you move your finger that way, friction is in that direction. Move your finger this way, friction is in that direction. Now, another form of friction is air resistance. Air resistance is another type of friction. It's not the rubbing kind of friction, but we call it air resistance. If you're an airplane pilot, they call it drag. Have you ever heard that before? Even in boats, they call it drag. Okay, I thought this was interesting. If you drive, even if you don't drive, maybe you looked out the window once you were on a highway, and you see these little things along the road, and they're in the ground, and these little pieces of corrugated metal are here. Have you ever seen that? Okay, now, these might keep you from going off the road. Let's say there's a ditch there. If you fall asleep, maybe you'll hit this barricade and all kinds of sparks will fly, and it'll slow you down a little bit. It will not slow you down very much because the metal in your car will hit the metal here. There's not a whole lot of friction there. You'll see sparks fly, but it won't slow you down too much. So, have you ever seen these on the highway? Well, that's a funny shape, isn't it? It's kind of stable. I like the fact that it's stable, but what's this all about? What are they trying to do here? Yes. Yes. Not have it hit the metal car, but have the rubber So what? The rubber tire hitting the concrete, that's a lot of friction. Now, I'm not an engineer, but I do know that they actually have an engineering units. They do all kinds of frictional tests, and they actually call, they have ratios, and they name, everybody names a ratio, and one of them is called the coefficient of friction. And you can look up the coefficient. What's the coefficient of friction between metal and metal, or between rubber and concrete? And it's high. It's really high between metal, rubber, and concrete. And so this was not an accident when they made this little cement thing. That'll slow your car down quite a bit, a lot. Now, another thing that they talk about is if I just have a book and I push it on the table, what's the theoretical idea of friction? And even though I take my hand and say, that's smooth, that's just because my hand says it's smooth, right? But in reality, if I look at microscopic, the table really is a bunch of mountains. So microscopically, there's a lot of ups and downs and ups and downs. And what about the book? Upside down mountain, see that? So it's almost like taking a mountain range here and trying to make it go across another mountain range. We just think it's smooth because our hand thinks it's smooth. I've actually seen some programs where engineers try to make a piece of metal, a table, they try to make it so flat that it had very little friction. They try to get rid of all these little bumps, and they have they try to move a thing across it, and it's almost like there's no friction. But that costs a lot of money to make one of those things. I don't know if there's a name. I don't know if there's a name for that. Okay. All right. Well, I want to show it to you. The next thing is I actually won't be talking about pressure, because we had a whole chapter on pressure. So if you want to read that, you can. And pressure is force per area. But we already had a whole chapter on that. I will mention this guy. This is actually the author of the book, Paul Hewitt. And this is one of his, they're both professors, but he said for a long time, this guy would help him on his, when he taught college class, he would come in and help him demonstrate. And even though I don't want to teach pressure, I'll teach you this anyway. Paul Hewitt's kind of he likes to be humorous and stuff like that. And so what they did is they put him on a bed of nails. So you have a plywood piece with like, I don't know, a couple thousand nails there, and they're sharp. Every nail's sharp. If you carefully lay down your back on it, the pressure on each nail is very small, because only a tiny bit of your weight is on each nail. So that's why you can lay down on the nails. Then they put another bit of nails upside down like this on top of you. And again, if you're careful, you lay them on there gently, the pressure per nail is very small, so it doesn't poke any holes in you. Then he takes a concrete block and he takes a sledgehammer and he says, what do you think will happen if I do that? You would think that would kill the person for sure. But he did say he stopped doing that after about 10 years, because if something were to go wrong, it would have hurt him. So he just decided to not do that anymore. But you could actually see these. Somebody online doing it, I bet. All right, somebody's making money doing this. But here's how they do this. All right, there are so many nails that the force per nail, or the pressure, is very small. You would think that this would drive the nails into his body, but this thing has a lot of mass, which means it has a lot of inertia. He also doesn't use a solid block of concrete. See the holes in it? He uses that kind. When he strikes it, a lot of inertia is going to keep the block right here. The block doesn't want to go down. It has a great tendency to stay at rest. So if he hits it right, a lot of the energy will be used to shatter the block, and almost none of it will be used to force the block down. And again, he cautions you that is very dangerous. He also makes a little joke, says, oh, Mom, I want to grow up and I want to be somebody like that. And he said, well, son, all you have to do is start out slow. Start out on a couple nails. Good or bad? Good advice? That's bad advice. Okay. So you don't start a bed of nails with start with only a couple, and then no, that would be bad. Okay, and also here's another thing that we did yesterday. Remember the cartoon we looked at? I was wrong. He did put the cartoon in this And so what happens here is, why is a feather and a hammer in a vacuum? Why do they hit the ground at the same time? And again, we talked about this last chapter. We'll do it one more time. Okay, so here's the feather and the hammer. So the acceleration on the feather is going to equal what? How do you find acceleration? Force over mass. Now, what is the force on the feather? That means it's weight. What is the force on the feather? Little force. How much mass are you trying to accelerate? Little mass. And what does that come out to be? It comes out to be 9.8 meters per second squared. Or you can say 10 if you want to right now. But what happens when you have the hammer? The hammer, what's the force on the hammer? How much does it weigh? It weighs a lot, doesn't it? But how much mass are you trying to accelerate? And those two ratios, so one more time, just for the last time, you had it last chapter. Little g is not the pull on anything. Just because little g and gravity start with the same letter, it's the acceleration due to gravity. It's not the pull of gravity, it's the acceleration due to gravity. You get that?
I remember that for the word.
So if you remember that, when somebody says, why does a feather and a hammer hit the ground at the same time? Don't say they're pulled the same. They're not. This guy's only pulled a little bit, and this guy's pulled a lot. Ooh, then I don't get it. Why would they hit the ground at the same time? Because they're accelerated the same. Why? Because acceleration is not just how much you get pulled, it's how much you get pulled per what?
Mass.
And that ratio is the same for all objects in a vacuum. Now, we did that last chapter, so I knew that we at least would review it again this chapter. All right, well, now I want to start the last part of the chapter, which I think is the most interesting. The most interesting, okay? Let's talk about what happens to objects that are falling and there is air resistance. Now, I don't know how much you know about this, but has anybody in here done any skydiving ever? Okay, now usually I don't get any, but every once in a while I had one student a few years ago, and their parents allowed them to go, and I let him do a little extra credit project. And what he did was he called 3 different companies that were close enough to here that if you wanted to do it one weekend, and he asked them questions. He said, how much would it cost if I want to do skydiving? How much would it cost? How old do you have to be? He had all the information. Okay, and then he said, what height, how high in the air are we when we jump out of the plane? And he wanted to know that because some companies will do this, and some companies will let you go higher. See that? And he'll say, well, how long will I be in the air? And the company knew that. You'll be in the air a total of this long and this long. How long will I be in free fall? I mean, before I pull the parachute. And then they told him that too. And so it was a great extra credit thing. If anybody's willing to do that, if you wanted to do it, again, you'd have to call the company. I don't know. Are they still doing that right now, skydiving? I would think they could. I think they could do it with masks. I don't know. But it was really interesting because each company had a different way of doing it. Some of them never did go above this height. And then some of them said, no, I'll take you up this high. And so we're going to talk about skydiving today. And I'm not sure how much you know about skydiving. It's not exactly free fall because there's air, but in a way, the first part of your dive is a little bit like free fall. They have some rides at Carowinds that are, one of them's called free fall, I think, isn't it? And so essentially, when you have a ride and you're up in the air and all of a sudden they let the bottom drop out, you know what that feels like, don't you? You felt that, right? And your stomach kind of feels weird, so what I want to do is let's talk about skydiving, and so if you'll need some kind of piece of paper here to write this on. Now what we're going to do, we're going to start at a certain height, and we're way up in the air, and we're way, way, way up in the air. Okay. Now, so let's say that I could use an airplane, but I'll wait till next chapter to talk about that. But what if you use a helicopter? Let's use a helicopter, and I don't have to worry about the plane going in that direction. So let's just use a helicopter. Okay, so we're in a helicopter, and the skydiver is going to jump out of the plane. Now, So let's draw a terrible drawing of a skydiver. Here's a skydiver, and here we go. There you are. Now, what I want to do is, this skydiver has forces on them. When they first step out of the helicopter, what force do you think might be acting on them? So everybody in this class should be able to tell me. What do you think? Yes, and what do we call that? What do they call the pull of the earth on you? What about the amount of gravity? What do you call it? Starts with a W. Weight. Okay, now, so I'm going to draw an arrow representing the person's weight. Is everybody with me on that? Now, he just stepped out of the helicopter, so he hasn't really encountered any air resistance yet. So my air resistance is going to be 0. Okay, because he just a millionth of a second after stepping out of the airplane, he hasn't really started to plow through the air. Now, if you read this, and I want you to read this tonight, it talks about scientists have studied what happens to objects when they're in the air. It says here, a feather and a coin fall with equal accelerations in a vacuum, but very unequal in the presence of air. When falling in air, the coin falls quickly while the feather flutters to the ground. The force due to air resistance diminishes the net force acting on the falling object. And then they talk about here, what kind of things cause you to have, if I was a skydiver, and what would you want to have more air resistance on you sometimes? Have you ever seen them die, like, I don't know, 10 different planes take off, and 60 different people jump out of planes, and somehow they meet up in the air? That's dangerous, number one. How do they do that? You jumped out before me. How can I catch up to you? And so if you know anything about skydiving, you can actually increase or decrease the amount of air resistance. If you want to put your hands out, see that? You're going to increase your air resistance. If you want to do a pencil dive, you'll decrease your air resistance, and that'll happen. And so you could actually catch up to somebody who has already jumped out before you, or you could slow yourself down and let them catch up to you. But it takes a lot of planning to get, 100 people all holding hands in these patterns, these little geometric. You ever seen these? And then they have to be careful because they have to get the picture, and then slowly the people on the outside, they push away. They want to get far enough away so when I pull my parachute, it doesn't tangle up in yours. And so the outside of the ring, get away. And then they start to change their air resistance. And then the next one's like that. And it can be very, very dangerous. So it says right here, it says the air resistance force, and that is a force, on an object experiences depends on two things. The speed, the faster you go through the air, the more air resistance you have. Everybody get that? The faster you go, the more air resistance, and your frontal area. They say area, but it says up here frontal. I don't care about the area back here if I'm a skydiver. That's not going to worry me. It's actually the frontal area that's in contact. See that? So when I say area of my hand, they don't really mean back here. They mean right here, right? So you okay if I say frontal area? Okay. All right. So anyway, let me draw the drawing again. Excuse me. Now, I want you to think. Now, you can do this. How much net force is on the skydiver when they first jump out? Let's see. This plus nothing equals what?
0.
Really? This plus 0, doesn't it equal this? Okay, so I'm going to draw that the same size, okay? Now, what do you know about the size of the net force? If we look at Newton's second law again, here's some detail. Ready? It's not force, it's what? Net force, isn't it? And the other detail is whatever direction the net force is in, that has to be the same direction of acceleration. You get it? Okay. Even if you're moving in the opposite direction, we're going to find that out here. So right now, this is the weight of the skydiver, and there's no air resistance, so the net force is pretty big. And so the acceleration will be kind of big in what direction?
Down.
So I'm going to put a great big old A representing that we have a huge amount of acceleration. When you first step out of the plane, the acceleration on you is huge. It's huge. Now, what I'm going to do is I ran out of, no, maybe I didn't. Do you have space for one more column or not? Okay, if you don't have one here, let's put it over here. So let's do a column for velocity, or you can say speed because we're going down. So what's the velocity right now? He first stepped out of the plane, just a microsecond after they stopped out. What's his velocity? It's like, whoa, Nina, little. So is he going very fast?
No.
No. Well, what's the acceleration on him? Huge.
Lunge.
Now, for those of you who still think that acceleration means how fast you're going, this is going to bother you today. Acceleration never tells you about how fast you're going. Is that right?
Yes.
All right, so now let's let the skydiver go down here, and now he's down here a little further. And what do you think? As long as he didn't, let's not get too personal. I was going to make a joke about defecating. I won't do it. Let's just say that he did not lose any part of his body. He didn't lose any part of his body. So his weight stays the same. Is that right? Is that right? His mass didn't change, so his weight didn't change. So now let's take a look. What about air resistance? Now, air resistance is a form of friction, and I'm picking up speed, aren't I? If I'm picking up speed, what happens to the air resistance? It starts growing, doesn't it?
Yes.
Now watch. And remember, it's always in the opposite direction of motion, right? Now, what's the net force now?
It's still the same.
Is it?
No.
This plus 0 is that.
False.
This plus that is also that? No, it's less, isn't it?
Yeah.
And now, what's the acceleration going to be?
Less.
Less. But what's my velocity going to be?
More.
Oh. Now, watch now. Wait. This is where you're going to get confused, okay? If I say my acceleration is less, does that mean I was slowing down? Be careful.
No.
I'll give you a clue. If you're accelerating at all, you're going faster, aren't you?
Yeah.
What if I have a little acceleration? I'm still going faster. So be careful about that. My speed is increasing, but the acceleration is decreasing. You okay with that?
Yes.
That's the hardest thing for you right now. Now let's go down to this point here, and this is kind of a special point. And a person's weight is still the same, but now he's really going fast. He's going really fast, and there's going to be a point where the air resistance is growing and growing and growing. It's going to actually equal his weight. Now, you remember in the first semester when, remember Archimedes' principle? It's like when an object's, when the buoyant force equal the weight, what happened to the object? So you put a boat in the water, it starts sinking because the weight is greater than buoyant force, and then it starts displacing more water. What happened when the weight equaled the buoyant force?
Then
Then it floated, didn't it? It was floating? Same thing happens here. It's not really floating, though. But what happens when your air resistance equals your weight? What is your net force? The net force is what?
0.
So that means you stop in midair, doesn't it? Thank you for not saying yes automatically. No skydiver stops in middle air. But this is a very special time for a skydiver because his acceleration is what? What's the acceleration? There's no acceleration. No acceleration. But what's my speed? My speed is as fast as it's ever been because I was accelerating. Now, I stopped accelerating, but what does that mean? Does that mean I stopped moving?
No.
It means I stopped increasing my speed, didn't I? So this is a very special place, and it's called Terminal. It's a terrible name. But they already made a movie with Sylvester Stallone, and so they're not going to change it.
Okay, yeah.
All right. So it's called terminal velocity. If you owned a company, you'd say, oh, you want to know how long it takes before TV is reached, terminal velocity. It's a terrible name because it makes it sound like your velocity is terminated. It's not. What was terminated? An acceleration. But they're not going to change it. They're still going to call it terminal velocity. Now, watch what happens here. At this point, you're going, and for some of you who still think that velocity and acceleration is the same thing, this has got to mess you up. The skydiver's speed is the greatest when the acceleration on him is the least. Whoa. Whoa. My speed was the least when the acceleration on me was the greatest. My speed will change faster than any time during the trip up here. But I just started. I just started my trip. That's why my speed's not very high. Here, my speed will not change. But you know what? I'm going really fast. So here's what's neat. A skydiver reaches terminal velocity. He will not go any faster the rest of the trip. Now, the bad news is, if you don't have a parachute, you will hit the ground at that really high speed, and you will die. You will die. Now, here's what happens now. Then the skydiver does something that he better do. He pulls the parachute. So what I'm going to do is pull the parachute here, and okay. So now he pulls the parachute, and remember the parachute was part of his weight anyway, so his weight is still the same. His weight is still the same. But watch now, this is interesting.
The air resistance a lot more.
Why?
Because the parachute is.
He has high speed, and he also has what now? Because he's connected, he also has more what? More what? Area. So now, wait now, it's going to bother you. The air resistance now is huge in what direction?
Upwards.
Now watch. Watch, this explains everything. The net force is what? It's pretty big in what direction? Oh. It's pretty big. The net force is big, so the acceleration is big in what direction? But wait. What if you're going in this direction, but the acceleration is in that direction? What happens? You slow down. That's the good news about a parachute. You get that? So now, I'm going to draw it again, because something else is going to happen. And I'm trying to draw the same bit. So now, something's going to happen. His weight's the same, and what's going to happen now is the air resistance will shrink. Now, my question to you is, why would they have less air resistance later on?
Because he's.
It's not because the area was decreased. What now?
Less speed.
Yes.
No,
What did this do to me? It made my speed go down, didn't it?
yeah.
And so what happens is people never talk about this terminal velocity. This second terminal velocity is the one that saves your life. I reach terminal velocity here, no acceleration. I will reach another point where there's no net force, meaning no acceleration. But what's my speed now?
Small.
This thing was slowing me down so quickly that my velocity went down to here, and now for the rest of the trip, I will have a new terminal velocity, which is small. So small that I shouldn't get hurt. Anyway, I don't know if this, I think this gets kind of interesting. All right, so let me put this up again. So there's a first terminal velocity. That means that's the fastest you'll ever go. Got that?
Yeah.
But then a second terminal velocity is reached at a slow speed. You get that? And then the rest of the trip, and you can ask the people, if you want to do the extra credit where you call the company, ask them this. How long are you in free fall? That means before you have to pull the parachute. Get that? How long before you reach terminal velocity? You can ask them that. How long will I be at this speed. And this will be, who knows, that could be another minute. You could be in the air another minute at that speed. You get that? But whatever that speed is, you don't go any faster all the way down. See that? But that speed's slow enough that you won't get killed. Now the book has, I think it has some numbers on here. Let's see if I can find it. Here they are. And so tonight I do want you to read this if you hadn't read anything, but it says, terminal speed can be controlled by variations of body orientation. A heavy skydive, we'll talk about that in a minute, heavy and light. Here it is. A parachute greatly increases air resistance, cuts the terminal speed from anywhere between 15 and 25. If you're, that's to be, 10 miles per hour or something like that. If you're going at those speeds, you probably won't die. You'll probably be okay. If you don't, unless you turn your ankle or something like that, you won't get hurt. But what is the speed before that? The terminal speed for a skydiver ranges from 150 to 200 kilometers per hour. That's pretty fast, okay? 100 is 60 miles an hour. 100 kilometers per hour is 60. So your terminal velocity is way up there, isn't it? And that's your first terminal velocity, but that'll kill you if you hit the ground at that speed. Yes?
People have survived free falling in a parachute.
We don't have that chapter right now on okay, let me see.
They obviously didn't hit the ground like directly.
Right.
So
Well, what can happen is one of the questions tomorrow on the worksheet I give you. Do you know why seatbelts work? And I'll give you it's something you're not going to think about. Seatbelts work because they don't stop you quickly. Seatbelts work because they don't stop you quickly. You say, no, I need a seatbelt to stop me quickly. Can I give you a clue? A tree will stop you quickly. Jump out of a building, the cement will stop you quickly. Is that what you want the seatbelt to do? No. You want the seatbelt to stop me slower. I don't want you to stop me in 100th of a second. I want you to stop me in 1/10 of a second. Take your time to slow me down. What about airbags? They're not meant to stop you quickly, are they? It's like, boo. See? If I stop you quickly, the force of impact is going to kill you. Why do you die if you jump out of a building and hit the ground? You don't die jumping. You die when you hit the ground, and what happens is what? You stop so quickly, the rest of your body plows into you, doesn't it? And the force of impact is huge. But what do stunt divers do? They jump out of a 10-story building, 100-story building, and they survive. How's that? These huge airbags. You ever seen them? They're huge. And they go, boom. So they decelerate over a long period of time, and that's why they don't get hurt. If you decelerate over a short period of time, you're going to die. All right, so let's do one more, and let's talk about a heavy and a light skydiver. What if they both jump out of the helicopter at the same time? And let's say that they both pull their parachute at the same time. Who's going to land on the ground first? That's a tough question. So I'm going to draw another skydiver here, okay? Let's draw a heavy skydiver. Okay, now he weighs this much. Okay, now, at the beginning, he also has no air resistance. So what's his acceleration going to be? It's going to be that much. See that? Is that correct? Okay, so if he has a greater net force on him, he's going to have a greater acceleration. So what's going to happen is, which skydiver is going, and let's say everything else is the same. The air resistance, everything's the same somehow. Who's going to reach terminal velocity first? Who is going to have their weight equal to air resistance first? This guy, or this guy? Who's going to reach terminal velocity first? Let's say these arrows grow at the same rate for both skydivers. Ready? I have a little arrow. See that? Who's going to reach terminal velocity first? I'll draw it. Okay. You don't get it. So his weight is still the same. But now the air resistance is like this number. Now what's the net force on it? it's bigger than this guy, isn't it? So he's still accelerating more than you are. And then you reach a point where the air resistance equals your weight, and what's happening to me? Here's my weight. And the air resistance is like this much. And guess what? I still have a net force, don't I? So when you don't have any net force on you, what about the heavy skydiver? He's still accelerating. So you'll be falling, and all of a sudden you'll say, I reached terminal velocity. Not me. I'm keep going faster. Okay, can we pull the puller shirts? Okay, then you'll never beat me because, see? So the heavy skydiver always reaches the ground before the light skydiver. Now, I'll show you a simple demonstration that's like that. Not in a vacuum. In a vacuum, these are both accelerate the same, but watch. Not even close. Not even close. Why? I want you to look now. I can tell you right now, that guy did not fall long enough to reach terminal velocity. That was still accelerating when it hit the ground. Watch now.
Oh, it's so accelerated.
Did you notice something? Like almost immediately after I let go of it, it has some speed, and it maintained that speed all the way down. You know why in the air, why does the feather never beat the ball? Because it reaches terminal velocity very quickly. I had more time to accelerate. I only had 1/10 of a second to accelerate, and watch. After I reached terminal velocity, I didn't have much time to accelerate, did I? So my speed never does get. So if an elephant and an ant jumped off a really tall building, same time, one of them's going to survive. The ant, who has more weight? Elephant. Who has more air resistance? Who has more air resistance per mass? The ant. So what's going to happen is the ant will reach terminal velocity within a second. And that means it didn't go very fast. The elephant may not even reach terminal velocity. It'll be going faster and faster when it hits the ground, and that's why it's going to splat all over the place and be killed. The ant will reach terminal velocity, take a long, long time at that speed to come down, hit the sidewalk, and walk away. Well, anyway, I think this is a very exciting part of the chapter. I hope you enjoy that. I do want you to just read it, scan over it, and we'll review tomorrow.